starting from now. So the CPU copy the data from main memory, okay, because it's an output device. So what the output device can do is the CPU gonna actually copy the data from memory into the device by buffer. Okay. The CPU copy the data from the main memory to the controller buffer. Okay. And issue an output request. And then the CPU basically pull the busy flag again. Okay. So let's just go back with this. Okay. Let me actually erase this. Now let's suppose this is actually the output device now. The controller is output device controller. Let's say like a monitor or display or printer, right? So if this is the output now, and then again, first, so the input, you basically, you start the operation and you ask the IO device, the controller, and eventually going to copy the data from the device to the buffer, and then copy the data from buffer into the main memory. But with the output, it's just the opposite. Okay, it's kind of opposite. You know, first the driver gonna copy the data from the main memory to the buffer. Okay. Once the copy is complete, then it can actually write the parameter. Okay. So it's probably going to say, okay, it's not read anymore, it's write, right? So it's a write data into the hard disk or whatever. So you set the operator, say, okay, please read the data from memory location 2001, okay, and put in the block 102, okay, to put in the block 102. So then you're going to say, okay, right. The opcode is right, and the data going to be right into from the memory location 2001 to 1002, and the opcode is right. Okay, so now the controller say, okay, I know what you want me to do. You want me to write the data into the device. So the controller gonna actually set the busy to true, and say, okay, you want me to write? So have you put the data in the buffer yet? Yes, it's in the buffer. So the controller start to actually copy data from the buffer into the device. Copy. Once all the data in the buffer completely copied to the device, then the controller gonna set the busy register to false and the status to success. Okay. Now during this time, while the controller is copying the data from buffer to the I/O device, then during that particular time, then the driver gonna keep actually pulling the data, pulling the busy register. Say, are you done yet? Are you done yet? As far as the busy register has a value true, then it's not done. So until the busy actually register becomes false, once they complete the copy and the data change to false, and then the driver going to stop the loop and start to read the status. And once the status is actually say success, and then the driver going to say, okay, this operation is successful. And then the driver may ask the controller to do the next copy, right? So then please actually read the data, just put the next data in there, okay, and just to set the opcode to 3001, and then write to 104, okay. So then it just repeat the operation. Okay. So this way you're gonna read the you're gonna actually output the data from the memory piece by piece to the device. Okay. So that's the output with pooling. So the output with pooling and the import with pooling, these are opposite operation. So import is basically, read the data and from the device to the buffer, and copy the data from the buffer to the memory. That's import. Output is you write the data from the memory into the buffer and tell the controller, say, okay, I have a data already written in the buffer. Please copy this data into the device, and the controller going to copy data into the device. Once it's done, then set the flag, set the actually status, and then the operation continues. So these are two opposite operations. That's called programmed I/O with pooling. Now we're going to tell what's the difference between these two. With the pooling, so that means even while the device is working hard, because when the device set to busy, it's working hard. Now the driver is also very busy, right? While the device is doing its job, the device controller is doing its job to perform the operation, and the computer actually driver is also busy. What is the computer driver is doing? What's the driver is doing? Driver is doing this while loop. Okay. Driver is keep checking the busy register. Okay. So the controller is busy and driver is also busy. So the CPU is also busy because CPU is actually running the driver, and it's keep checking the busy register. Now, this is sometimes a waste of CPU cycle, right? Because when the I/O device is busy, and then the CPU is also busy running the driver, and the driver is doing nothing but just pulling the data from the busy register. So that's a waste of CPU time. So that's why sometimes people come up with another approach called program I/O with interrupt. Okay. So in this case, the I/O device still going to be the same in terms of the configuration or structure. However, the I/O device is going to have a capability of sending interrupt. I hope you still remember the interrupt, right? The interrupt is some kind of a message sent to the interrupt controller, and then the CPU going to read the interrupt vector, and it starts to execute, right? So it's the interrupt basically means, okay, so the interrupters are used for the I/O processing. Okay, so the interface to the controller remains the same. So there's no difference between the program I/O with pooling and the program I/O with interrupt in terms of the interface, I/O interface. However, this time the controller is equipped with the ability to issue interrupts. So the controller can send the interrupt to the CPU. Okay, now how does this work? So now you're going to see using the program I/O with interrupt. Okay, so the first step it's still the same. Okay. So the CPU executing the driver can start a new I/O operation when the device is ready, which is determined by reading the busy flag. So it's the same. So when CPU trigger running the device driver, and device driver gonna check the busy register. If the busy register say, okay, it's false, the value is false. So that means I'm not busy. And then the next step are going to be the same as program the IO with pooling. So the CPU basically write the parameter to the operands register and then write the data to the opcode. Basically tell the controller what to do. So the controller going to basically copy the data excuse me, from IO device to the buffer. Okay. Oh, sorry. The controller need to set the busy register to true. Just tell the other system say it's I'm busy. So then it's actually start to perform the operation. Okay. Now once the operation is done, it's basically change the busy register to false and change the status to success if the transfer of the data is successful. Now during the controller, while the controller is doing its job, copy the data from IO device to the buffer. Now the CPU gonna actually block the driver. So the driver gonna be blocked. So instead of pulling, it basically the driver is keep doing the loop, right? And checking the busy register to see whether the busy register actually is still busy, or if it's not busy, that means the operation is done. Then I can do the follow-up operation. So the driver is actually not doing the loop. The driver gonna be in a sleep mode. It's blocked. Okay, so CPU block the driver. Now, the problem is, in this case, once the controller finished the job operation, copy the data to the buffer, how could the controller tells the driver saying, well, I'm ready, I'm done? Because the driver is asleep. Okay, it's blocked. Because when the program was pooling, because the driver just keep reading the data, the busy register data, and the driver actually once the busy register change the value to false, then the driver immediately know in the next loop say, okay, the busy register now is false. So the device is ready. So I can actually perform the next operation, like copy the data from buffer to the computer memory, right? I can do that. But the driver is asleep. So it's not actually pulling the busy register. So in that case, with interrupt, then once the controller finished the job, and the controller want to inform, the controller need to inform the driver, say, I'm done my job, please do your work. Okay, so that's the next one. So the controller gonna send an interrupt to the CPU saying, I'm done with my job. So please actually, wake up this driver. So the driver actually, when the device completes the data transfer into the buffer, the controller write a success and a failure in the status of of the stat operation into the status register. That's the same as the program IO is pulling, except the driver is not keep actually doing the loop. So the device controller need to set the reset the busy flag to false, and the controller issue an interrupt, which reactivate the blocked process. Okay. So once the process, once the CPU resume the executing, and you're gonna actually copy the data. You're gonna check the status, whether it's successful or not. If it's successful, then copy the data from the buffer into the computer memory. So in general, the operations between these two, I/O operations are basically the same, except in the pooling, the driver gonna keep actually checking the busy register. Now, with the interrupt, the driver put himself in sleep, and then the controller need to send an interrupt and wake up the driver, so the driver can continue to actually check the status and copy the data. These are two differences. Now, what's the advantage of the programmed I/O with interrupt?
I guess you can like have well, when the driver is like becomes blocked, something else can use the CPU when it's blocked, and you're not like I guess wasting your CPU resource by like repeatedly pulling the busy
Okay.
flag.
That's a great point. Yes. Okay. Yes, I think yeah, William, right? So you're right. That's exactly the point why you want to use the interrupt in certain case. Not always the case. Okay. We will actually we will discuss the pros and the cons for each of the approach. But definitely with the interrupt, you blocked the driver. So the driver actually in a sleep mode. So the driver is not using the CPU. So that means the CPU can actually do something else. Okay, so that's the advantage of using the interrupt. Now with the pooling, because the drivers keep actually using the CPU cycle to pull the data, pull the busy register data. So that's the difference. Okay. So now if you want to tell what's the real difference, if you use any real life example, it's just like if a manager ask if in a company a manager asks employees to do a job, and then the manager assign the job to the employee, and while the employee is doing the job, the manager that basically keep actually every like 5 minutes, manager go to the employee's cubic and they say, are you done yet? And the manager said no. The employee said no, and then the manager come back, and then manager come back and say, are you done yet? Are you done yet? The manager just keep actually ask you know the employee whether you have done or not. So that's like a pooling, right? Now, the interrupt is that the manager gave the job to the employees, and the manager going to do something else. Now, the employee, while doing the job, once the employee finished job, the employee basically make a phone call or whatever, send an email to the manager, say, hey, I'm done. It's just an interrupt to the manager. Okay, so that's interrupt. Now, it sounds like interrupt is better than pooling, but not necessarily the case. Depend on. Sorry, if you hear the background noise. Okay, it depends on the type of job. Okay, if type of operation. Now, if the operation is like a bursty in natural, it's very quick. I think pooling is still kind of good, because if you actually the CPU actually trigger the driver, and the driver basically asks the I/O to perform the job. But if the I/O is a very, very fast I/O device, it can basically do the job in like a couple of microseconds. Then I think pooling is still a good option. Okay, because the operation itself is very quick. Now, if you want to use it with the interrupts, remember interrupts is also very costly, because interrupts takes time. remember the whole process of interrupt, right? So the interrupter basically need to, when you do the interrupter, you need to save the data into the actually process control block, and the one process, the driver need to actually, um, once the driver actually, when you put the driver into sleep, then when CPU actually stay away from the driver, CPU need to store the current information of the driver actual process into the control block, in the process control block. And then CPU gonna do something else. And when the interrupt comes, it's gonna, read the data again, just, you know, all the actual processed information control block from the control block into the CPU registers. So the interrupter itself can take a lot of time. So this is actually kind of situation that if, the process itself, if the operation itself going to take like a couple of microseconds, okay, that's a time for the process. Now, why the interrupter going to take a lot of time? Okay, so then you will find out it's costly, because you prefer that you waste of the CPU time over here, okay, during the pooling. Now you waste of CPU time. But with the interrupt, you basically, so you're done. So you're not do the pooling. So you're in a sleep. So CPU is free at this time. But when you do the interrupt, CPU is actually busy over here. Okay. So it just matters that you know, if if the operation itself is very short, I prefer to let the CPU busy during the operation. Okay. But for slow I/O, some of the I/O operations is very slow. Like if you read the data from a floppy, read the data from um, some kind of maybe the hard disk, okay? Because hard disk requires to read the data from the magnetic disk, and then you need to actually rotate the disk to the right position. You need some kind of mechanical movement, so it's kind of slow. Okay, in this case, maybe interrupter is a good idea. Okay, if the operation takes like a 1 second, interrupter itself only takes a couple of microseconds. It's still worthwhile to do the interrupter, because you don't want to waste the CPU for 1 second. Okay, you prefer to use the CPU in this one couple of microsecond. Okay, so it's kind of trade-off, but depend on what kind of operation you want to perform. Okay, here let's check the uh, okay. We will compare these two pooling and interrupter later, a little bit later. But then there's another kind of I/O operation. It's called I/O with direct memory access. So direct memory access, basically you in a computer, in modern computer system, for many operations, the computer have a piece of hardware called DMA. Okay, so DMA actually, it's a using DMA. So if, for example, the computer actually CPU gonna deal with a kind of I/O device that gonna be repeatedly perform the same operation for a long period of time. So it really doesn't matter which approach you use, or programmed I/O with pooling or programmed I/O with interrupt. Now, if you perform with a long period of time, pooling is definitely a bad idea, right? Because if during this long period of time, the CPU is always busy pulling the data. So it's not a good idea. interrupt is not also not good idea because pulling every time when you actually fill the buffer, you're gonna actually send the interrupter, and then you're gonna actually fill another buffer because the data is so big. You're gonna repeatedly perform this job. So if the operation is gonna repeat it 1,000 times, so you need to actually perform 1,000 times and generate the interrupter 1,000 times. Each time when the operation is done, then you need to send the interrupt. Okay. Now, one of such an example is, for example, if you want to read some kind of a video. Okay. So if you store a video, like a high def video, uh, 4K video in your hard disk, and you use your software like a player, you know, movie player to play the movie. So you're gonna play this movie, 4K movie, for like 2 hours. So now when you send the data from, when you display the movie, so you basically need to copy the data from hard disk, one block of data from hard disk into the buffer controller, and then CPU need to copy the data into the memory, and then you need to actually send to the output to the monitor. So you need to keep actually copy the data all the way from the computer hard disk and eventually display on the monitor. And you cannot copy the whole movie, right? It's so big. So the device buffer, I don't think the device buffer going to be bigger enough to hold the whole movie, right? So you have to send the movie into piece by piece into the movie. Actually, you split the movie actually file into piece by piece and put in the buffer and send to the monitor. Put in the buffer, send to the monitor. Now during this time, you're gonna keep doing this job. That's really bad. So that's why in this case, now they have a dedicated device called DMA. Okay, direct memory access. So in this case, when the CPU start to actually run the device driver, and then the CPU realize, okay, this is kind of operation, so I need a DMA to help me. So the CPU gonna program the DMA, say you're gonna take care of the job. So when the CPU actually you know, do this, send to the device driver, and then the the next step, the DMA gonna pick up and do the job. Now this is actually how the job are gonna be done. Okay. So again, so when the device is not busy, CPU write the parameters to. So the first step, again, the device driver gonna check the busy register, right? If the busy register says I'm ready, so the CPU start to read the, write the operand and operate in opcode into uh, the operand register and opcode registers. Okay, and then the second one is the CPU start to operate by writing the opcode. So this is done into the opcode register. The driver process then block itself. Okay, and then the controller gonna start to work. So controller put the busy register to true and start to copy data into the buffer. And then without direct access, you know, so then the job is done, the copy the data from the I/O device like a hard disk into the buffer. Once this part is done, then you're gonna send the interrupter to the CPU, and the CPU start to copy the data to the memory, right? But now the controller gonna actually send the data to the device DMA, okay, direct memory access controller, and direct memory access controller gonna take care of the job. So the direct memory DMA is just like a smaller scale CPU. Okay, but it's a very simple device. It's not like a general purpose CPU. It's just do the special job. It's just to keep doing the same job again, again. So when the buffer is full and send to the DMA and send DMA copy to the main memory. So the CPU never going to be involved. Okay. So because the driver um, is blocked. So the DMA actually is busy, and then just keep doing this job. Okay. Now, depend on how the DMA is set. In some case, the DMA is set, they use a counter in the DMA to set to say, okay, please repeat this job 30 times. So the counter is set to 30 times. So then that for next 30 times, the controller gonna fill up the buffer one time, and the EMA copy to the memory, and fill up the buffer a second time, copy to the main memory, and so this gonna repeat 30 times. So each time, once the job is done, the counter is reduced by one. So the counter is initially 30, and then after the DMA perform one job, the counter reduced to 29, reduced to 28, and eventually reduced to 0. Once the counter actually reduced to 0, and then the controller gonna actually interrupt the CPU, say, hey, I'm done this part. Okay, so what's next? And then the device driver may actually, repeat this process again. So, so you can set a very big counter if you know the application is going to take longer. So this is a very good idea when you actually, you know, perform any kind of movie, play a video. So then you're going to repeatedly pull the data from the device I/O and put in the buffer and send to the memory, and put in the buffer, send into the memory. So it's just a repeated job. Okay. So it's not worthwhile to waste the CPU time. So that's basically DMA. Uh, so 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 basically the DMA gonna perform the job repeatedly until it's done. Then it interrupts the driver, the CPU, and wake up the driver. Okay. So that's the direct memory access. Okay. I think I'm almost done. This is the last slide I want to talk about. So here's the difference between, or the comparison between pooling and the interrupts. And pooling and interrupts both result in overhead during I/O processing. But the source of overhead is different. In the pooling, the overhead is the pooling itself, right? So you keep the CPU actually keep pulling the data. So the CPU is busy. Okay. However, the pooling is itself one single pooling it's a very simple process. Okay, it just require only few machine instructions, couple of machine instructions, just one, because it's just run the while loop, right? So you just read the memory. No, I'm sorry, read the busy register. So read the busy register, read the busy register, read the busy register until the busy register change the value to false. So that's pooling. However, it just requires few machine instruction, but you may actually perform hundreds or thousands or even 10,000 of times. So you're probably going to perform 10,000 poolings during the I/O operation. So each pooling is actually very fast, but you may actually perform 1,000 times or even a couple of 100,000 times. Okay. However, on the other hand, blocking and later reactivated process using interrupt, it's actually constitutes significant CPU overhead. Okay, you block the driver and then you activate the driver each actually requires some significant time. But it's predictable. So that means for each operation, you just need to do it once. Just block it once, activate once. Okay, using the interrupt. But this operation takes a lot of time, a lot of actually a CPU overhead. Now, it's basically just something like you block, take that much CPU time, activate, take that much CPU time. So then you take that much CPU time, right, for the interrupt. Now, pooling is each pooling take a small amount of time, take a small amount of time, take a small amount of time. Now, if actually your operation is very short, you only take like a couple of actually 100 pooling, and the total time is still smaller than the interrupt. Pooling is better. Okay. Now, if you actually the operation is very long, so you're gonna keep pooling, and you're gonna pull like a millions of times. Then the total time is still bigger than the interrupt. Then in this case, interrupt is better, right? So it's just like a trade-off, depending on what kind of operation you want to perform. Okay. Okay, I think that's pretty much all for today. I'm actually almost done with the I/O. I think I'm gonna stop. So on Thursday, I'm not gonna spend the whole times for the teaching, but I will make it like a question and answer sections, or like office hour, so you can actually ask me any questions about final exams, about assignments, so anything. So the the things that I want to resolve everything before May 11th. Okay. So the cutoff date is May 11th. If you have any issues with assignments, final exams, anything, we have to resolve before May 11th. Okay. So this Thursday, if you have anything you want to talk to me, just feel free to actually come. But first we're gonna actually complete and finish up the couple more slides, and then I'm done. Okay. Okay, I think that's pretty much all for today. Do you have any